Good afternoon, everyone. You're right. Good afternoon, everyone who joins us online as well. Today we have Dr. Kublai Khan Ali Mirza to give his talk about exciting talk on leveraging P2P botnet principles for enterprise solutions. I'm going to give you an overview about Kublai. In case you don't know him, for those who don't know who he is, he's a renowned expert with a rich background in network security, cloud computing, and machine learning. His insights are grounded in over a decade of experience in industry and academia, making this an admissible opportunity for everyone interested in cutting-edge cybersecurity trends. So I'll hand over to Kublai, and I hope you enjoy the talk. Thank you.
Thank you, Zainab. Good evening, everyone. Welcome to the talk. Thank you for the kind words. Zainab didn't know I was an expert, but just sharing the research that I do. Just apologies in advance. I'm recovering from a severe chest infection. So if I start coughing abruptly, it's not because I want to cut it short. It's just my throat is not agreeing with what I'm saying. The topic, excuse me, is decentralized security solution leveraging the P2P botnet infrastructure. So let's start. So the agenda for today's talk is what is a botnet? We're going to give a brief description of what botnet is. We're going to briefly discuss how P2P botnet work, how they're different from the conventional botnet and their infrastructure, and what's unique about their infrastructure. And then we're going to talk about the problem, the security problem faced by heterogeneous enterprise networks, and how we can leverage the P2P infrastructure to actually propose or use a decentralized security solution for such networks. So a botnet, as the name suggests, it's driven from a robot and a network. So robot network or network of zombies controlled by one command and control center. In fact, network devices spread mainly through Trojan, but it's not limited. Funny enough, most of people here physically present are my advanced malware analysis students who I was just talking to half an hour ago or 45 minutes ago about the same thing. So yeah, it's not, the lines are quite blurry. It's not just Trojans that are being used to deliver that, but yes, it's spread mainly through Trojan, used for DDoS, spam, and many other operations, such as, for example, you might have heard of, definitely heard of WannaCry, which was also a botnet, and obviously it was a ransomware as well. There are two main types of botnets: centralized and decentralized. So centralized IRC bots, HTTP. This decentralized ones are the really dangerous one, which are the P2P based. Anyone here who's used a P2P or a torrent, you don't have to say it out loud, just, nod twice. We'll talk about it in a minute. Traditional botnet, centralized architecture, as you can see on the on my right, your left. This diagram, one command control center, one domain, and multiple bots controlled via that domain. A bigger diagram on this side where you've got a bot master, command and control, communication channel, again, on a single domain with multiple servers, and then you've got multiple bots being controlled by single command. Does it make sense? Do you understand how it works? Simple enough. When I say simple enough, yes, the infrastructure is simple, but I don't mean that the botnets are not lethal or the mechanisms that are used to actually proliferate or propagate the payloads, they are not lethal, they are lethal. So the WannaCry was based on this particular infrastructure. Yeah, it's oversimplification of that, but just to make you understand how a botnet works. Infect machine, botnet, bot or zombie, we call it. A bot master, cyber criminal, creates a command and control center. Command and control center, also known as the mothership, which actually controls and delivers the commands or the commands that say what kind of operation you need to perform. So for example, again, if we take WannaCry into consideration, if a ransomware like WannaCry infects your system, it doesn't mean that it immediately is going to, stop your machine or encrypt everything. It waits for the command to be delivered, and then it does the job. Because encrypting one machine, it's not the ideal approach, right? It's not the main purpose. The main purpose is to infect as many computers as possible. Then, obviously, it wants to propagate laterally in the network and up the hierarchy and in the network in the while as well, as much as possible. Multiplication, again, propagation, a mechanism of propagation through spam, email, inspected websites, social media. All of these are delivery mechanisms, not the infection technique. There's a difference between the two. So infection techniques, what kind of vulnerability it exploits, what vulnerabilities are there that the malware is exploiting or is expert in exploiting. These mechanisms are delivery mechanisms. These techniques are delivery mechanisms through which the payload is delivered, and then the rest is done by the payload. And then it works in a cycle in order to proliferate in the wild. So peer-to-peer botnet, as the name suggests, it works on decentralized mechanisms. The mechanism we saw here was more centralized as compared to what we have in peer-to-peer. So if I explain in the context of torrents, again, you might have used or heard of torrents. So torrents, you are downloading a movie, or somebody is downloading a movie, not specifying anyone. Or let's say if you're downloading the latest movie and it's a few GBs and the file is there, the file that you'll download for the torrent will be a very lightweight placeholder in a way, right? And then that will be loaded by the tool which actually runs the infrastructure or is part of the infrastructure. And then there are contributors who hold that file, and then different packets from those contributors will be extracted. The more contributors there are, the faster the file will be gathered and downloaded by you. And obviously, they're not obligated to stay or contribute. They can opt in and opt out, right? That's the infrastructure. Obviously, that's just the infrastructure. That's not how a P2P botnet works. It operates like this, but obviously, the bots are obligated to participate. This is what's on my right-hand side is the architecture. So client bots are similar to what the zombies were in the previous architecture that we saw. The servant bots work as a domain. So if we go back and look here, the domain, there was single domain, right? So in order to break that infrastructure, you take down the domain and the bots become clueless to who to respond because there's no direct connection between the command and control center and the bots, right? Which in this case is quite different. Any idea? So we saw domain in the conventional in the conventional bots, which is not the case here. We saw domain.com in the diagram, which means it can be a server somewhere. But here, they are servers, but they are not public servers, right? They are similar to the client bots that we have here. How are they similar? They are part of this. They can be part of this network, but logically separated. How are they logically separated? They are logically separated. because they are identified as server. So those particular bots that are considered client, they receive their commands from these servant bots. Okay, so when they receive the, and it's based on, again, an algorithm. Every malware has its own, but generally a leader election algorithm is quite commonly used, right? We're going to talk about that later. So yeah, the servant bots are identified as the ones who get the command, who send the command, and they are working as domains. Why is it, and it is problematic or difficult to actually take down the infrastructure of P2P botnet as compared to a conventional botnet? Any idea why? Anyone? The domain that we saw in the conventional bot is a public domain, and it can be taken down and it can be stopped. These are legitimate machines, legitimate computers that are part of a network. If you take down one, it's already identified which one will be the next server which will act as the servant bot, right? And it's decided between the algorithms, and that is already encrypted in the client bots. So bots are divided into two main, client and server. We talked about what client and server and the difference between the two. Now, if we look at the operations of P2P botnet, I know it's a lot of text. Unlike conventional, there's no centralized server needed. Bot communication with each other to retrieve commands from botmaster. Botmaster uses asymmetric encryption in some of the malware, and in some, they use symmetric encryption. So asymmetric encryption is public-private key. It's encrypted using the public key, private key of one, public key of one, and then decrypted using the private key of the other. And the malware that use symmetric encryption, they use AES as the encryption mechanism, and they use Diffie-Hellman to actually transport the key. So botmaster keep one key, secret private key, and embed the other key in the bot, public key. Botmaster can use the key to encrypt commands, and then bots can decrypt them using the public key. Some modern P2P botnets use AES for symmetric encryption and the Diffie-Hellman for transportation. So just to give you some context, imagine there is a network like one of our labs, right? And there are 60 PCs. Half of the PCs will be designated as servant bots, but only 2 or 3 of them will be live servants, and one of them acting as an actual domain, right? However, that domain has already identified who the predecessors, who will be the ones taking place. So that domain, if it goes down, or let's say one of the students is leaving for the day and they shut down that machine, right? The next one in line will come up, send the encrypted message to the rest of the bots and say, yep, that's the master. And when that one becomes live, it has already identified, it knew the third one, but now it knows the fourth one as well. So when the first one comes live, it has already identified the next 2. And whoever goes down gives control to the next one in line, right? And all of that information is encrypted on the machine and in the bots as well, without them knowing. They only know that this is something we need to encrypt, which has a message, which one is next in line, and they can compare with the command coming from the server. So yes, you can take down one of the, I've discussed it later as well, one of the ways to take down this infrastructure is through peer poisoning, but that peer poisoning has a solution as well from a negative point of view, of course. So it has decided to die on me. Sorry about that. So P2P botnets only work if there are enough nodes, because obviously it needs to identify X number of servant bots, Y number of clients in order to work successfully. The bad news is because the nodes are legitimate computers, they can't simply be seized like a server you can take down in a conventional botnet architecture. Each node server maintains a list of IP addresses to other nodes, which it shares with the client bots. So the infrastructure knows who's part of the infrastructure and who's not part of the infrastructure to avoid any new node to be included without it being infected by the bot, by the botnet. Nodes are required to maintain and share a list of other nodes. It is impossible for the bot master to manually add new nodes. It needs to be infected by the machine, become part of the infrastructures. But nodes can add other nodes automatically. That's called lateral propagation. You might have, if you are a Marvel fan, I'll often make movie jokes, but the dialogue associated with the diagram is if you take down one head, 10 more heads will pop up. So it's similar to that. So the leader election algorithm, that's how it works. So if you take down the leader, it has already identified 3 more leaders. And if you take down the first 3 leaders, it has already identified the 4 other leaders that are part of that network. And as I mentioned, that they are legitimate computers, they cannot be, yes, they can be isolated again, but the entire network will be down. So dismantling peer-to-peer botnet, peer poisoning, introduce a malicious computer into the network. By introducing malicious computer means that is not actually malicious, because we are poisoning a malware. So it's a computer which pretends to be malicious, but actually identifies the list of infected computers and identifies the actual servants that are controlling the nodes and communicating with the command and control center. And that will enable to take down the infrastructure. Contains a list of other malicious nodes, separate the servant from the legitimate node, the actual malicious bot network. And after a while, the client bots will have no servants because it will eventually take down the infrastructure or the bridge between the command and control center and the network. Some of the powerful P2P botnets, Game Over Zeus, Mirai, Zero Access. Mirai is an IoT malware. Skype, obviously, is not malicious, but it works in the same manner and uses the same infrastructure. So the problem now, I mean, so far we discussed what botnet is, how peer-to-peer botnet works, how they're different from conventional botnets, and now to discuss the problem, why we discussed all of that. So securing heterogeneous enterprise network, or HENS. It's not an actual term, I'm just using it to. So HENS are comprised of the following: devices with different hardware and software configurations, devices that are not homogeneous. It can be different operating systems, different hardware configurations, and so on. BYOD, you are all aware of the term, what it stands for: bring your own device, or in other words, bring your own disaster. And the reason why it's bring your own disaster, because obviously it can have anything, it can be infected, it can have any software configurations, and if you are attaching it to a network, to an enterprise network, it can compromise the entire network. And that's one of the biggest problems in heterogeneous enterprise networks. Require multiple security solutions because we are talking about hardware and software devices with multiple configurations, with distributed configurations, with heterogeneous configurations. So we need multiple security solutions as well. And in most of the enterprises, there are centralized solutions which require centralized hardware resources as well, which is a big problem because it has a single point of failure. This is one of the biggest problems. Even if it's a cloud-based solution, there are the entire infrastructure is, in a way, on premise, it is centralized. And obviously, it can be easily compromised as well. So the solution, a P2P inspired decentralized security framework, which we call a node-to-node recovery model. So node-to-node recovery problem, what problems we have? Locally hosted and resource-intensive security solutions, cost-intensive scalability, lack of accurate malware detection, low detection rate, multiple tools requirement for enterprise security. Solution, lightweight, minimal digital footprint, and intelligently scalable presence. Autonomous, self-evolving, and personalized solution, decentralized and spread across different devices. The research is comprised of 4 phases. So phase 1, phase 2A, phase 2B, phase 3. I'm not going to talk about the first 3 phases. I'm going to talk about the last phase, phase 3, which is actually phase 4. Obviously, it's built up all the other phases to phase 3, and phase 3 is actually the backbone is based on the first 3 phases, but here I'm talking about the node-to-node recovery model. So I'll just briefly touch upon what the first 3 phases were. So phase 1 is cloud-based intelligent malware detection. It's the engine where the malware detection happen, and the model at the user's end runs the instance of the engine that is on the cloud and trained and tested there. Phase 2 is cloud-based network anomaly detection. Again, it's another feature in the node-to-node recovery model supported by the cloud backbone. Phase 2B is the multi-cloud based intelligent network security. This is with an organization, and I can't reveal a lot about that. Phase 3 is the node-to-node recovery model. So this is phase 2A, design and implementation, which is based on 2 types of data. One is tactical threat intelligence. The other is heuristical threat intelligence. So on the my right, your left, is the network data, which the training and testing is done via clean and malicious data and based on some. So I'm not going to spill the ingredients of the secret sauce, but just the diagram. We've got clean network traffic and the malicious network traffic, and we've got different machine data analytics techniques. We've got IOC, indicators of compromise, and we've got IDS data in a clean technical analysis repo, and then the similar kind of data for malicious technical analysis repo, and which is then trained and tested in a technical training and testing module. And then we've got heuristic threat intelligence data. Again, we've got clean and malicious repos, which are, and we've got a customized feature extraction tool, which extracts feature from both the files, and then the algorithms are applied, and then we combine that in the combined intelligence report. So that was phase 2A, kind of the backbone of the security model for identification and prevention and detection. 2B is, I can't talk a lot about it, but it's multi-cloud based intelligent network security. Basically, what I talked about in 2A, it's that distributed over multiple cloud platforms without end user knowing which cloud server or location it's coming from. And they have multiple cloud service providers, and it intelligently distributes the task and creates it over the network. Excuse me. Phase 3 is something that is relevant to today's talk. So node-to-node recovery inspired by serverless architecture. So for heterogeneous critical networks, avoid single point failure powered by cloud-based intelligent detection engine and multi-cloud hosting. So this is some like brief diagram what it looks like. So it looks pretty centralized, but the server that everybody is connected to is part of the main network as well, and it's not a separate server, right? And different network devices are connected to that server because it's running the lightweight instance of the cloud-based engine. But the same instance is present on all the devices, but only controlled at this in one point in time by one servant bot. The analogy for the P2P bot. When the algorithm identifies the server as the first or as the leader. At the same time, the second and third in line are identified, and they are embedded with that encrypted file, which enables them to, once this goes down, the number one, the leader, gets unencrypted and identified that whether I am in line or the next node is in line, right? And sorry, and as soon as the first one goes down, everybody then gets connected because they have that embedded message in their storage as well, that which is the next one to connect to, right? So that security is working on all those devices. And yes, at one point in time, there is one node which is running that security mechanism or controlling the security mechanism or identifying at the same time which device might be compromised. And if the device becomes compromised, other than the server, it's isolated, and the device next to it cleans the device in isolation. This is the pseudocode, just brief. I'm not, again, going to talk about the details of the algorithm, but initialization of the election process, failure detection, a node detects that the leader has failed or there is no current leader. There's a step before this one as well, but that's the critical step, and I'm not going to talk about how it actually uses the data and what technology we are using to actually identify how to embed and how to look for and what information to look for and how to crawl for such information. But again, so once the leader goes down, a node detects that the leader has failed or there is no current leader, election initiation. The detecting node initiates an election. This node sends an election message to all nodes with high IDs. And that is then, that identifies how many nodes are currently available. The significance of this step, or election initiation, is really high. The reason, we are in a legitimate network. Assumingly, we are in a legitimate network, and we know that there are X number of devices. However, since we are talking about heterogeneous enterprise network and BYODs, there can be a variance in how many devices were previously available and how many devices are now available. So that's the first point why this step is significant. The second point is because similar to a P2, how we can bring down a P2P botnet by peer poisoning, same thing can happen here as well to bring down a legitimate network. So only the files which have a particular kind of encrypted element in them, again, that comes in the step that I've not mentioned here, only those nodes can become part of the network, right? Only those nodes will participate in election initiation process, right? And that way, so wait for the responses, the response comes back encrypted with the IDs, again, randomly generated numbers. There's a separate algorithm for that. And then receive reply, timeout if the response is not received from a particular node which was previously present. So there can be two reasons behind it. One is that it was a BYOD and it doesn't, it no longer exists in that network vicinity, or it's been taken down. Both are relevant. And obviously, if there is no response, they are removed from the list. And when they join in, they are treated as a fresh node, and they require the whole authentication process. Declare leadership. If a node wins the election, no active nodes with higher IDs, it declares itself as a leader. The new leader sends a victory message to all of the nodes, acknowledgement. Other nodes acknowledge the new leader, and the algorithm terminates. And then optional branch. If the current node receives an election message from a lower ID node, it sends an acknowledgement back to an issuing node. If the current node hasn't already started an election, it initiates its own election and becomes part of that. And then all the other things apply, and they are populated with whatever the requirement is. It's the algorithm. It is just a mathematical representation of what I just said. Node-to-node architecture performance results. Not talking about the if you take down that, or if you take down that. This is the impact on the network in comparison with the conventional antiviruses and security mechanisms. So we tested around around 10 antiviruses and security and enterprise security solutions. And this is on the x-axis, you've got the percentage of the CPU resources being used. And as you can see, nearly all of them are either 30% or above in consuming CPU and network resources, which includes bandwidth as well. And on the top, the hosting model is consuming at max in one instance 5% of CPU power. And it's not just that, because a counter argument can be somebody might be paying, for example, the cloud server. This is AWS at the same time where the cloud engine was hosted, which is the backbone of the recovery model. And as you can see, the highest point it touched was 2.5% of the EC2 instant it was running on. We span it out to 24 hours with a 15 minutes window time. Right, so that's the comparison of the CPU utilization in the real-time detection. So the recent results, this is with respect to a particular multiple malware. And again, this is a particular malware that we identified, which was it identified the family. And this identification was done on the node itself. The lightweight node we are running was able to identify the family with the fingerprint, along with the vulnerability it was exploiting. As you can, sorry, I just pressed the stop button. Yeah, so as you can see, the vulnerability it was exploiting, right? This is another malware. It's confidential. It's something that the partner I was working with, so I can't share the fingerprint, but this is the vulnerability was exploiting, and the node was able to identify what vulnerability it was identifying, and the family, all that. I mean, obviously the family is not known because not a known malware, so that's why the family still, the family tag says unknown. So to conclude, we talked about the types of malware. We talked about the operations of different botnets and the requirement of security in a heterogeneous enterprise network, and how we can leverage from the P2P botnet to actually benefit the heterogeneous enterprise networks. Thank you for listening. Any questions? Thank you. Anything? Yep. So are you asking that what type of network in real life it can positively affect? So for example, our university one. So our network is heterogeneous. There are two networks that we are running here. One is our wired network, which has our lab connected to and all the workspaces that we have. And then we have a wireless network. The wireless network, our machines are connected there as well. And the laptop that I bring in, even though it's a university issue laptop with university's different services running on it, it is connected to the wireless network. And then I've got my phone connected to the same network, and the devices you bring, like your phones and your laptops, are connected to the UG Rome network as well. So it is quite heterogeneous. So this is the kind of infrastructure that will really benefit from this sort of thing, because on this network we have a lot of times IT identify actual malware running on the system, not just my system, but students who don't know that they have malware on their system, and they've been contacted by IT that you can bring in your laptop and we can fix it for you. So that's sort of, and obviously there are other students who bring their laptop that is not infected, and that's how malware can propagate, because they are on the same wireless network. So this is one of the examples, and a quite close one as well for us. Make sense? Does it answer your question? Any other questions? Yep.
You kind of bring your own device procedure. Does it work the same with Wi-Fi? Say, how to plug my laptop in, before. Would the kind of whole process be the same there, or would it be given through Wi-Fi, say, protocols to,
With respect to this solution? Yeah, it's different. Okay. The reason why it's different is because and there's a policy. For this solution, we've got a distributed PEP and PDP, policy enforcement point and policy decision point, which actually applies to these two kind of devices. So if it's connected to a wired network, which means it has more privilege in a way, because it's connected to a network which has more servers connected to it. So therefore, it can only be connected if it passes a particular policy where the PDP and PEP come in, and that has a separate policy layer, which means that if a device is connected to that and it's participating in the election, means there is an ID associated with it, which enables them to directly register to the election. Whereas if a wireless device is being connected, it has to go through a separate certification process, which involves encryption protocols to be matched with the device, and then move from there. Yeah, no problem. There are more problems than the solution. Yes, that is correct. And that's where the scoping comes in. Obviously, we're still working on it. But the solution, did they mention what kind of problem, what particular problem? So yeah, the problems are definitely more than the solutions. And even the problems that I've listed here are more than the solutions we have proposed. But it covers most of them in a way that addresses the overall scope of the solution. So if you can ask what particular problem they are addressing, and I'll be able to answer it more accurately. Yep.
So say a botnet managed to get through these defenses and it started propagating. What are the defenses in line that once it started propagating, stop the spread?
Okay, yeah, very good question. So the solution in general is not just for botnet; it's for any malware. So if you are asking if a botnet is trying to benefit from the heterogeneous enterprise network, how will it work? It will work in what we did in phase 1 and phase 2, because the engine, and as I showed in the result here, this malware here that we have identified is not a known malware. WannaCry is a known malware, and even the conventional antiviruses will be able to detect it. However limited they are, they'll be able to detect WannaCry because it's very popular, and the family is quite known, and the variants, regardless of how many millions of variants of WannaCry are there, conventional antivirus will be able to detect it. But this malware here was a customized one, not known to public, it's not known to antivirus, but we were able to identify, our security model was able to identify it as malicious. And that's so, regardless of whether it's a peer-to-peer botnet or conventional botnet or any other type of malware family, this here is the solution where an unknown malware can be identified, because we are using, so as I showed here, sorry, yeah, the security solution is based on two techniques. One is kind of a conventional, but on steroids. The other one is the technical data, and both are using machine learning algorithms, a combination of machine learning algorithms to detect it more accurately. So there are heuristics involved. Yes, there are fingerprints involved, but there are more behavioral-based analytics that are involved in order to detect and accurately detect, not just detect, so because there is a fair chance of false positives. And it's not efficient if you are detecting a lot of false positives because it's not usable anymore, right? So it has to be inaccurate. So that's how we accurately detect it. Thank you.
Would that be the same if it was, say, network traffic? Obviously, botnets make use of like denial of service attacks. Would that apply the same standards regardless?
Yeah, because on the left-hand side, that's why we're using the technical and network data, because on the right-hand side, that's the file heuristics. File heuristics change as soon as it hits the network. It completely changes as soon as it's network. And if it's a metamorphic or polymorphic malware, then heuristics don't matter. They can change, and the fingerprints don't matter, because with every iteration, everything is changing. Even if you are changing a dot in a file, it changes the signature completely. So that's why we have this, the technical network data, which actually uses the network indicators to train and test the models. Thank you. So locally hosted and resource-intensive security solution, cost-intensive scalability, lack of responsiveness in prevention, lack of accurate malware detection, low detection rate, multiple tools requirement for enterprise security. These are the problems that I listed. So locally hosted and resource-intensive, it's a lightweight security solution distributed across the nodes, which means that it's not centralized and it's not using a single server to actually host multiple security solutions. Not that multiple security solutions won't work, they will work, and this can work alongside. Obviously, there are trust issues, and the more security solutions you have, enterprise feel more secure, but this is the solution with respect to that. Cost-intensive scalability, obviously, if it's just a node-to-node recovery model, and the main engine is hosted on the cloud, scalability becomes more flexible and efficient. Lack of responsiveness in prevention. This goes back to the question James asked earlier about whether if there's a distributed botnet trying to attack it. So it doesn't need, even if the connection is disconnected from the cloud, it locally has that mechanism to detect malware, and that I showed in the last slide, where we identified a malware accurately without going back to the cloud and verifying whether it is a malware or a legitimate file. Low detection rate, again, that is the answer that I gave earlier as well. Multiple tools requirement for enterprise security. As I said, I mean, there is no obligation on an organization not to use multiple, but the level of accuracy and the network-based approach we've shown and displayed in the results as well, it has the potential to replace multiple security solutions. So these are the questions or problems that I raised, and it addresses, the proposed solution addresses all of them. Yeah, the list is shorter of solutions, but it addresses all of them. Okay. Yeah.
When a leader is chosen, everyone is connected to that, and from what I could understand, at the moment that it's a leader, it chooses next leaders as well, and if there's some crisis or attack or so on, it asks them to be leaders, for instance, correctly?
No, the leader doesn't choose the next in line. The algorithm chooses the leader. The leader doesn't know in itself, it's not plain text that these two are the next leaders. The next two leaders know that we will be the leaders. But as soon as that leader goes down, the next in line pops in because the continuous communication that I'm the leader now.
supposing that every leader is a separate server instance or something?
Every leader is part of the network. So like the lab we have, let's say the lab 101, we've got 67 or 60 odd computers in it. If we are running that machine over there, and we did use that as one of our tools one of our environments to test that. If we are using that, then 3 computers from there will be part of the leader clan. And once one of them goes down, the other one will pop up saying, I'm the leader. Yeah. This one? This one? Yeah. So this is just an illustration of the P2P botnet infrastructure. So, and that's exactly what I was talking about when I was answering. No, this is not my solution. This is the P2P botnet infrastructure, how it works. So what it's illustrating is what I was saying earlier as well. So there's a pool of, there's a network in a single organization. It doesn't have to be a single organization, but kind of the same level, and but legitimate computers, and some of them are the servant nodes, and most of them are the client nodes. But again, they're all legitimate computers. They are not a separate domain. So that's what it's illustrating. It's based on this. It's based on this. And the idea is that the actual engine is behind the firewall because it's on the cloud. It's on the cloud. But the instances of it are running on the nodes. And then one of them is acting as a server. And then the leader. So, thank you. Any other questions? It's running on the network.
So if you want to break down the system, then you can identify the next leader and probably take down the system.
So I want to say something that I didn't say earlier, just to answer your question, because that's part of the secret sauce as well. Consider blockchain and breaking that down. I didn't want to say it, but I can't answer it without saying it. See, that you can't reverse engineer that. That's how we're doing it. Thank you.